Have you ever wondered what's the way to torture yourself so much to make high voltage in the most inefficient way possible? Well, here today I'm gonna show you just how you're gonna do that. And here on this table, this is a side effect of this process, is everything you'll need to do just that. So welcome to Starborn Science. This is everything you'll need to know how to make an ineffective Class E oscillator. Let me show you step by step how you're gonna torture yourself like I did for the past 4 days of my life, making the oscillator I call now D4 for the 4 days gone from my life. And I totally mean 4 days. 1, 2, 3, 4 gone. So you'll need a choke that's an 100 microhenry choke. You'll need some capacitors, low ESR, polypropylene or polyester metallized film. I use 200 nanofarad capacitors, rated for 1600 volts. One prototyping board, one big fat slab of aluminum heatsink because of the switching losses, one beefy 10 ohm resistor, ceramic, one 2 watt 10 kilo ohm resistor, one silicone pad because it's not needed but I use it, one plastic washer thingy because it's not needed but I also use it, one screw to mount your FET on the plate, one IRFP 460 FET because that's the only fucking FET that works with that setup, as I've found the hard way by blowing about 30 euros worth of FETs, and one power input clamp and one clamp to clamp your FET, and solder, and a screwdriver, and a light bulb to, well, show off your city low voltage RF field, and a resonator coil which you will wind yourself. This is 50 turns of 0.08 millimeter wire around the CFL tube, which is 2 centimeters in diameter, and a feedback coil with 0.50 millimeters of wire wound the same direction as the resonator coil for giving feedback to the MOSFET gate. Oh, and the best part, don't even think trying to scope this without getting your scope probe at 10x. You're gonna blow your scope input. I'm just telling you this. Do not try scoping a Class E oscillator, even if it's not working at ZVS mode. You're gonna blow your damn scope. I'm telling you this because it's happened to me in the past, and thank God it was a cheap ass scope, a handheld one, worth like 100 euros. So I'm just telling you this, do not do that. That's a fair warning right there. Okay? Okay. So let's build this thing and let's see. So yeah, let's go over this thing very quickly because it's fucking crazy. So you have the choke over here, which just filters the RF out of the circuit. Don't just ignore it. We feed the VCC goes into the drain of the MOSFET, and here we have our, ignore the feedback for now, we have our main L2 and C1 capacitor, which is our resonator coil, and our 2 capacitor, which is drawn as one capacitor since they are 2 capacitors in parallel. And these two resonate, forming an LC tank, which the values of these two dictate the resonance frequency due to the formula of the resonance frequency being what it is. And yeah, we've got a pull down resistor between gate and source. Do not even think adding a Zener diode because you won't be able to jumpstart this circuit. And we have a 10 ohm resistor rated for 2 watts, and you'll see why it's rated for 2 watts. And now you'll see we have a feedback loop going around the L2 main resonator coil, which takes feedback and gives it to the gate of the resistor, and the other is connected to ground, of course, to complete the connection. And as you can see, when you first connect the circuit, ground and VCC, they are just a floating voltage between ground and drain. So in order to jumpstart the circuit, it's like getting an old diesel car from World War II and cranking the ignition and try to get it started, because you'll see that live, because there's no connection directly to the gate, so you constantly connect the gate to the VCC manually until you jumpstart the oscillation, and then the circuit starts oscillating. And then you can add a breakout point from the emitter, from the drain, to actually get your electric field. Now the electric field grows in voltage as the frequency is lower, because there is more energy per pulse, and decreases as the frequency increases into the megahertz range. Now I've tuned personally my oscillator, this in my case is 12 microhenry, and this capacitor is 200 nanofarad, and my resonant frequency is 400 kilohertz. So it's not an RF oscillator really, because in my mind RF is over the megahertz frequency. But if I went there, then there wasn't enough voltage to excite plasma in a fluorescent tube, so it wasn't good enough in my eyes. However, the RF field was there, and it was there strong enough to cause my speakers to buzz, and certainly enough to fry electronics. So do not bring any electronics whatsoever close to this kind of device, even if it's not tuned to run in ZVS mode, because this is not running in ZVS mode, as I mentioned earlier, which is sad because it's really inefficient. And yeah, that's about it. So to the next one. So as I said, if you hate yourself as much as I do now, you will follow my steps one by one. And so we begin by soldering this 3-legged clamp on the breadboard, on the prototype board, sorry. As it's very possible you will go through quite a few MOSFETs trying to get this to work. Hopefully you won't, but hope has never helped anyone in this world. You know? If you know, you know. So that is soldered. Now I will go ahead and connect the 10 kilo ohm pull down resistor that goes from gate to source. So there you go. This is connected now to the clamp where you're gonna connect your FET, and I've made a solder line from the drain and use a lot of solder. As I said, they're gonna be a couple of amps at about 20 to 30 volts, so they're gonna be about 80 watts going through this thing. So yeah, use a considerable amount of solder or it's gonna melt. And yeah, now let's add the choke. And one leg of the choke is gonna go to our drain and one is gonna go straight down and to our power input clamp, like so. Here's the choke and here is our connection. VCC in, into the choke, into the FETs drain. Now let's add the gate resistor, which is, well, it's self-explanatory. It goes to the FETs gate on the left side of the clamp where your FET will be connected. If you don't give a crap and you do not want to use a clamp, go for it if you're a true masochist. I suggest going with a clamp. And here is our gate resistor added. As you can see, connects to the gate, and over here which will be connected to the feedback coil. And now we will add our two 100 nanofarad 1600 volt capacitors, which are polypropylene capacitors. I say that again, they must be low ESR capacitors, otherwise they will get fried because there's lots of amps. So here are our capacitors connected with in parallel, of course, with the MOSFET's source. Now we'll take this beautiful contraption, which is the solenoid resonant inductor, and we will be connecting this in series with the resonant capacitors over here and the MOSFET's drain. And the resonant inductor is added. As you can see, one end goes in series to our capacitors and one end goes to the MOSFET's drain, and this is our feedback wire. And as I said, this phase goes to the gate and this phase goes to the source of the MOSFET, to the ground. Okay, so let me connect this. So as you can see, this side of the feedback wire goes to our MOSFET's source and this goes to our gate resistor. And now we need to connect the ground wire to our ground, and the circuit is complete because, as I said, there's no direct connection to the ground to the gate of the MOSFET. There's only an inductive magnetic connection which will be only available when the oscillation is started. Till then we will only be able to jump start it manually, and you will see how that goes. So this is the circuit completed. So now you'll actually see what it takes to start this thing, which involves doing this, like trying to jumpstart a car from the World War II. And you either get a burn from the RF field on your hand or see the power supply jump to 2 amps. So after I don't know how many tries, I've spent 5 minutes short circuiting the gate with the drain of the MOSFET. It actually started oscillating. So now, as you can see, we have a pretty strong magnetic electromagnetic field. The meter almost maxes out at 50 microamps near the oscillator. You can light up a CFL bulb and keep it lit. With the electric field. First we have to excite the plasma by touching it to the breakout point. And then we can drop the voltage and still keep it lit. We can also, I guess, try to but not successfully for some reason ignite neon bulbs, which is really strange. But if I place it in the resonator coil, you can see that it does light up. quite really nice. I don't know if the same goes for the thing, but no, it does not. Same goes for an LED with an inductor on it. It glows near the resonator coil, but it also glows if we touch it over there. Now I can also try doing something else. I can try and add a small Tesla coil and have this breakout point act like sort of a primary. And see there, if I get the ground of the Tesla coil and touch the fluorescent bulb to it, it lights up. If I add the top load on top and touch the fluorescent bulb, it also lights up and stays lit. Let me get the camera for you up to showcase that. If I get my meter close, it maxes out a lot easier now because of the Tesla coil magnifying the effect of the thing. And yeah, that's about it. And to show to you guys how powerful that magnetic field and that electromagnetic field that this thing produced was, I'm gonna show you what my Tesla coil that draws 200 watts produces. At this range, which is about 30 centimeters. So the electromagnetic field produced by this little circuit is quite intense. That little note, I want to add that. So yeah, keep that in mind. So yeah, I hope you enjoyed it. I hope you learned something. I hope you enjoyed my torture. And if you wanna get tortured yourself, you can of course always try replicating it. And yeah, keep exploring, keep dreaming, and I will see you on the next one.